So, hello everyone, and welcome to the Green Power Future Mission's National Pilots webinar series. This is the second in the series, and today we'll be hearing from the International Renewable Energy Agency, or IRENA, about their innovation landscape for smart electrification. And I'm delighted to be joined by several colleagues from IRENA, and I'll let them introduce themselves in a moment. But first of all, for the benefit of those who may be unfamiliar with Mission Innovation and the Green Power Future mission, I'll go through a few slides about that just now. So Mission Innovation was launched in COP21 in 2015 and is the main intergovernmental platform for accelerating clean energy innovation, involving 23 countries and the EU represented by the European Commission, as well as several collaborating organizations such as IRENA, who we'll see today. And these members are responsible for over 95% of public clean energy RD&D investments globally. Now, Mission Innovation, or MI, is structured around 7 missions, which are public-private innovation alliances that are setting goals that will lead to tipping points in the cost and scale of clean energy solutions. You can see the 7 missions of Mission Innovation on the screen, but we are the Green Power Future mission, and so I'll talk a little bit more about that now. So the GPFM's goal is to demonstrate that by 2030, power systems in different geographies and climates are able to effectively integrate up to 100% variable renewable energy, or VRE, in their generation mix while maintaining a cost-efficient, secure, and resilient system. And we do this through knowledge exchange and capacity building, demonstrating innovative solutions and generating the tools, data, and networks needed to enable more regions to be powered by affordable VRE. Like all of the other missions, the GPFM is a public-private partnership made up of in-kind contributions from its member countries and organizations. Italy, China, and the UK are the co-lead countries, and you can see the many other members that we have in our coalition from around the world on the screen here. The GPFM splits its work across 3 main pillars. The first pillar is led by China, focusing on the generation of the variable renewable energy from the likes of wind and solar power. The second pillar, which is led by Italy, focuses on the grid, system flexibility, market design, and regulation. And the third pillar, led by the UK, is focusing on the data and the digitalization for the electricity system. Now, I'll quickly talk about the GPFM's first flagship project, which is the 5 Demos in 5 Continents project. So the goal of this project is to establish 5 large-scale demonstrations of innovation activity in the 5 continents of Asia, Australia, Europe, North America, and South America, which can demonstrate up to 80% VRE integration by this year, 2024. These demonstrations are made up of 80 national pilots on the scale of millions of euros and aimed at reaching technology readiness level 6 to 7. Each of these national pilots is tackling one or more of the 50 most urgent innovation priorities identified by the mission and driving towards the 80% VRE integration. And you can find out more about all of these pilots in our National Pilots Report, which you'll find published on the GPFM section of the Mission Innovation website, where you'll also find more of our core documents such as action plans and annual reports. So on to today's agenda. As I mentioned before, the main goal of the GPFM and Mission Innovation in general is to facilitate knowledge exchange between its members and any other interested parties, to catalyze and accelerate innovation around the world. And so that's why we've set up this webinar series, so that all of you, the pilot project leads, and any other interested innovators can discuss ideas, progress, and lessons learned along the way. So this is supposed to be quite a relaxed exchange where some project leads will give short presentations, and then we'll open the floor to the audience for some fruitful discussions. And then lastly, just before we get started, I want to show you the webinar schedule as it stands so far. So last month we had a very interesting webinar from Brazil talking about hybridization of their isolated systems in the Amazon region. And you can find the link to the recording for that on the GPFM website and also on our LinkedIn page. And then today we are featuring IRENA speaking about their innovation landscape report. And then in the following months, we'll hear talks from Spain and also colleagues at National Grid. So keep an eye out for updates on those. And lastly, just some quick pieces of housekeeping. Please use the Q&A function to submit your questions at any time throughout the talk, and we'll get them at the end. And also feel free, if you like, to raise your hand, and you can be unmuted, and you can ask your question verbally if you like. And with that, I will hand over to Francisco from IRENA to get started on the webinar. Francisco, the floor is yours.
Thank you very much, Craig. And let me start by thanking Mission Innovation and the Global Power Future Mission for the invitation to present our initiative on the innovation landscape for smart electrification, which is also providing input to the GPFM on different documents, and as you mentioned, Craig, this demo, etc. Next slide, please. So to give a little bit of context, first of all, IRENA has been and continues to be very supportive of mission innovation as a key international initiative to promote R&D for the energy transition. And in particularly, we see the great importance of the Global Power Future mission, because as we will see later, the future will be mainly electrified. So this initiative plays a key role in disseminating the latest innovations and trying to advance action all around the globe in advancing on this smart electrification pathway. We as IRENA have been supportive also of this particular mission in different ways, as mentioned, also providing input to their different documents where they present case stories, demonstration, pilots, etc., but also providing guidance on how the mission may have even higher impact through the technical advisory group of mission innovation. Also, recently at more political level in Dubai, in the COP28, we jointly organized a session on developing countries benefiting from the knowledge gathered by mission innovation, and particularly this mission also using IRENA's network to connect this mission with emerging and developing countries that may benefit. More recently, for example, with the African Union, where you see, for example, the picture that is from that event where we had the privilege to have Luciano Martini, our friend there, representing this mission and connecting with this network. So we are and we will continue to be very supportive of the Global Power Future mission. Next slide, please. And this is so relevant because, as you can see on this slide, on the left side, you have the energy mix, the global energy mix as it is today. As you can see from the total final energy consumption, only around 22% is in the form of electricity. But if we look at what it should be by the mid of this century, if we want to meet the 1.5-degree scenario aligned with the Paris Agreement, electricity would play a much more relevant role. So direct electrification should represent more than 50% of the total final energy consumption. But you also see a dark green box there, which is the hydrogen share in the final energy mix at global level, and it says 14%. And actually, that's mainly also electricity through production of hydrogen via water electrolysis. So actually, around 65% or higher should come from electricity. So as mentioned before, electricity will be the king of the energy vectors in a decarbonized future. Next slide, please. But the challenge is quite significant. If we see this bar chart, basically it shows the electricity consumption at global level. And today we are in around 25,000 terawatt hours of electricity consumption globally. By 2030, this should increase almost 70% to close to 40,000 terawatt hours. And by 2050, in a 1.5 degree scenario, it should basically triple from today to more than 70,000 terawatt hours. If we see the boxes, the color boxes on the last bar, which is the 2050 scenario aligned with the Paris Agreement, we see, for example, the light green box, which is the production of green hydrogen. So it says that basically just for production of green hydrogen, there would be a demand close to 20,000 terawatt hours, which basically is the whole electricity consumption today. So let's imagine it's basically like if all the electricity that is produced today in the planet would be used by the mid of this century just to produce green hydrogen. Around half of the total electricity produced today would be for electric vehicles, which is the purple box. And in industries, it would be also a significant increase. So electricity, renewable electricity, will certainly be key to decarbonize the energy system. But we have to be smart on the approach to actually electrify all this end-use energy demand. Why is that? Basically, from the demand side, there will be new loads connected to the system, like electric vehicles, heat pumps, electric boilers, electric arc furnaces, electric crackers, and so on and so forth, electrolyzers for production of green hydrogen. So there will be a huge new demand and new loads that will be connected to the system. On the other hand, we will need much more variable renewable power generation, also injecting electricity to the grid, of course, with the challenges of variability and weather dependence. So on the supply side. So it means that we need to find an approach where basically, instead of having loads that may constrain the power system, these new loads become sources of flexibility for the system, facilitating the integration of this huge additional amount of variable renewables that need to be connected to the grid. And that actually is what we call the smart electrification approach. It's an approach where you electrify those loads, making these loads not constraints to the grid, but actually new sources of flexibility for the grid. Next slide. And this has also a big implication in terms of the investment or the cost of this energy transition. What we see on the screen is an estimate of how much would be needed to be invested in basically infrastructure, electricity grids, and flexibility options for the energy transition. And is in the order of $1 trillion per year. Yeah? If we think, for example, what is the GDP of a country like, for example, a medium-sized country like Colombia, for example, it is in the order of $300 billion. So it means like is the whole economy of a country like Colombia 3 times every year is what would be needed to be invested in electricity infrastructure and flexibility. And if we don't go with a smart approach, but we go with an uncontrolled load approach, this investment may increase between 3 and 10 times fold, so between 3 and 10 trillion per year. So it means that actually a smart electrification is not like an option. Basically, is the only way to go ahead if we want this energy transition to really move forward. Next slide, please. So that's why innovation is so critical, to really find the technologies that can help to implement such a smart approach where, for example, digitalization, storage, etc., will play a key role. But it's not just about innovation in technology. We would need to accompany that with innovation in new market design and regulations that compensate such a flexibility and providers of such a flexibility. We need a new way to operate and optimize electricity systems, and we will need new business models for the private sector to invest and get revenues and profits from these new opportunities in power systems. So we need this systemic innovation approach to actually unlock this smart electrification approach. Next slide, please. And that's why IRENA has come with this innovation landscape for smart electrification, because there is no blueprint. Every power system, every country has a different power system architecture. It has different constraints, different sources. Some have hydropower, others don't have hydropowers, others have access to solar radiation, or wind, etc. So every power system is quite different. So you cannot have a one-size-fits-all solution. But what you can have is a toolbox. And we have created this toolbox with 100 innovations, again, in technology, market design, business models, and system operation that countries can use as building blocks to create their own smart electrification solution, as my colleagues will explain in a moment. But as you can see, innovation is really the foundation to really make this energy transition happen in an affordable, sustainable, and reliable way that we ensure affordability and energy security for each country. And that's why we see this Global Power Future Mission critical in helping countries to disseminate this knowledge and good practices. I would like to stop here, and now I'll hand it to my colleague Arina, who will explain a little bit more how countries can use this toolbox. Thank you.
Thank you very much, Francisco, for this perfect introduction. It's my pleasure to, and hello everyone. It's my pleasure today to lead you through some insights of this innovation landscape for smart electrification report that IRENA launched last year. And in this webinar, we will focus on the toolboxes that we developed for power to mobility and power to heating and cooling. So first on power to mobility. We already know that in terms of technological innovation, the electric vehicles are key for decarbonizing road transport. IRENA analysis suggests that today we have around, or in 2022, we have around 10.5 million electric vehicle passenger electric cars on the road worldwide. And we need much more of this to be aligned with Paris Agreement and decarbonize the road transport. In 2030, we need to reach 360 million, and in 2050, more than 2,000 million. As Francisco mentioned, this will increase substantially the electricity demand that these electric vehicles will need to will need from the electricity grid. So here are a few just orientative numbers from Bloomberg. Electricity demand from all EVs is expected to reach around 4,000 terawatt by 2040, in comparison to only 100 terawatts that they were using in 2021. As well, the charging network infrastructure, it's a very important component, and a lot of charging network infrastructure needs to be developed for these electric vehicles. So that's why we want to show and to create a blueprint, a toolbox for countries to understand how they can incentivize smart charging of electric vehicles and smart electrification of the mobility sector in general. Here is just a study that was done by the TSO in Belgium, ELIA, showing how much smart charging of electric vehicles can help on the grid and can shift the load, the peak load, from evening peak load to midday or to during the night time. So you can see that minus 13% from the evening peak load can be decreased, and that means decreased grid congestion and minimize grid investments needed, and also use more variable renewables, integrate more variable renewables in the grid, using the solar generation available during the day, or wind generation that is more abundant during the night. This all can be done with a smart charging approach of the electric vehicles. We are aware that the smart charging strategy differs from the type of mobility and from different, we call them segments. So we identify these 5 segments on the mobility, 2 and 3 wheelers that are mostly deployed, and we see them in developing countries, in global south, and their smart electrification strategy will be very much different than the smart electrification strategy of passenger cars in global north, for example. Then we have light commercial vehicles, heavy duty vehicles, which are vehicles that are driven by commercial and business. So their parking times are much less. The duration of the parking time is much less than the passenger cars, for example. So that changes how and where they will be charged. And finally, the electrification of city buses, which have a very specific route, and also their parking times are very precise. So we look at all these e-mobility segments and show how different innovations and different strategy can be applied for each of these cases. This is the innovation toolbox for power to mobility. It includes 35 innovations. As Francisco mentioned, we mapped innovation in technology and infrastructure, and also innovation in market design and regulation, system planning and operation, and business models. Just to go very quickly to what we see on the screen. So in the report, we have a description of each of these innovation and some examples and how can be implemented one by one, but just to give you a flavor of what is there in the technology, we look basically at the technology of electric vehicles, including also the battery, then charging infrastructure. There are different types of charging infrastructure available, digitalization, which is a key in a smart charging. Then on the regulation side, we look at the new innovation on electricity market design that are needed to incentivize the behavior and the smart charging, but also on the regulation on the charging infrastructure to incentivize the development and deployment of charging infrastructure, which we saw it's quite substantial. Then strategic planning between mobility sector and power sector and cooperation, it's very important. And also innovation in smart operation of the power sector with high shares and high, a lot of electric vehicles integrated in the grid. And last but not least, we have innovations in business models that shows different services that the EVs can provide to the power system and can get remunerated for that, and also different models to enable EV deployment. Of course, as I mentioned, not all these innovations need to be implemented at once. There are some with higher priorities and some with less priority. There are some that fits better some types of vehicles and some segments of e-mobility, and some that others. So for that, we have also created a guidance for policymakers on how to navigate this landscape of innovations. So we created what we say the kits, the innovation kits. We have 3 kits: the essential kit, the smart charging kit, and the mobility segment kit. And each kit includes a number of innovations. The essential kit includes basically the starting innovation, the innovations that any policymaker should look at to start deployment of electric vehicles and start. The strategy should start with looking at these innovations, and then building upon on the essential kit in the smart charging kit. Here, it's a bit different whether the strategy is unidirectional charging or bidirectional charging. Bidirectional charging is generally more complex. It has added value, but sometimes unidirectional charging is enough. So an assessment of what kind of smart charging strategy should be done from the beginning. So you can choose the proper technology for that and then go for the right incentives. And then there is the mobility segment kit, which differentiate between personal vehicles and fleets. As mentioned, also the strategy is very different because of the parking times and the duration of the parking and the location of the parking and the number of vehicles that would be connected to the grid. Fleet has a very big potential to send more services to the grid and get remunerated for that on a larger scale. Very briefly here, we show the case of California. We looked into that. California is one of the most advanced regions or jurisdictions in terms of deployment of electric vehicles, and they have a very solid and interesting plan for smart charging of electric vehicles. And we looked at different elements and different projects that they have in California and see how that fits with our innovation toolbox. So we created their strategy based on our toolbox. You can find also a bit more details in our report on what we found interesting in California and how it was important to combine all these elements. They are looking not only on deploying the charging infrastructure, but also they have a lot of projects in smart charging, and also the cooperation of all the stakeholders are like nicely done through a grid integration working group. And they also have a new V2G grid code, vehicle to grid code, and different innovation and regulation as well. And for this, the last slide for the power to mobility focuses on blind spots for policymakers. In our research and interviews and discussions with all the stakeholders for collecting this data and putting together this innovation of landscape innovation, we noticed that there are several blind spots that we wanted to bring attention to, that they are very important and oftentimes overlooked, especially by policymakers. So first, smart charging does not necessarily mean bidirectional charging. There is a lot of value only from implementing unidirectional charging in some places and some power sectors. This would be enough, and it's also much easier to implement. Development of charging infrastructure should not mimic the petrol filling stations and not focus only on fast charging. New changes in the behavior needs to be also encouraged on the consumer side. Then it's very important to ensure that charging infrastructure is standardized and interoperable, especially when you cross a lot of borders by driving, and it's important to have access to the charging infrastructure anywhere. Then planning of electric vehicle charging infrastructure should be inclusive and reflect the local settings. It should not be only for people that have the luxury to have their own garage, but also for people that live in crowded cities and apartments, and they park their car on the streets. This should be well considered by policymakers. Then mobility trends needs also to be considered in electrification strategies. There is a tendency to move from personal car to sharing and mobility, car sharing. So this also will change how the smart electrification strategy is implemented. Then co-locating the EV charging with solar generation minimize a lot the impact on the grid. So this has a lot of potential, especially for parking lots or office parking. And last but not least, state agencies should coordinate and maintain consistency, especially that this is a coupling between two main sectors that have never been coupled before, transport sector and the power sector. So consistency, it's very important to receive similar and consistent signals for both sectors. Now I will lead you through the innovation landscape on power to heating and cooling. Again, the main technology for electrifying heating and cooling are heat pumps. Why? Because they are highly efficient. They provide heat at temperatures required in buildings, and they can also be used in the reverse mode for cooling. Today, IRENA analysis suggest that we have in buildings around 58 million of heat pumps, and we need much more to be aligned with Paris scenarios. As you can see in the graph, by 2030, around 450 millions, and by 2050, almost 800 millions. This is in buildings, but also the number of heat pumps in industry needs to grow from insignificant, less than 1 million today, to almost 80 million in 2050 to electrify heating in industry. As with power to mobility, on power to heat, we also have different segments, and their smart operation strategies will differ. If we have district heating and cooling, it's very different than building sector and very different than industry sector. The main difference is in the temperature that needs the temperature needs. So in district heating and cooling and building sector, it's a lower temperature, while in industry sector, normally their temperatures require more than 100 Celsius or even more than 150. And for that, the technology of heat pumps is quite different. And then the size. Industry sector and district heating and cooling, they will have medium to large heat pumps. And in building sector, there are small individual heat pumps needed. And of course, for the space heating, the demand is very weather dependent, while for industrial processes, the demand is driven by the business. So there is a different level of flexibility and smartness that could be applied there. Again, this is the landscape of innovation for power to heat and cooling. It includes 35 innovations in these 4 dimensions. Very similar to the mobility, we look at the technology, what are the conversion technologies that are emerging and available. Thermal storage, it's also an important technology that offers a lot of flexibility, and it's often also overlooked. And different innovations in district heating and cooling systems and digital technologies, again, very important for smartness. Then what are the innovations that we see on the electricity market and other incentives and regulations in the sector, heating and cooling sector, the planning of these 2 sectors and the operation of this coupling of these sectors. It's also very important. So we identified a number of innovations there, and the business models. Here, maybe one of the most interesting categories is the waste heat recovery models, which deserves very special attention in minimizing the waste heat and using it further. Again, not all the innovations are equally important or equally fitted to everybody. So we created these kits to guide policymakers on how to build their strategies according to their needs and the sector they would like to tackle. So we have an essential kit with the innovations that basically are essential, like the starting point where they have to look at. And then we have different kits for heating and a different kit for cooling. And in heating, we also have a different strategy that can be applied for heating for buildings, where as I said, the heat pumps are smaller and a bit different than the district heating, where the heat pumps are much bigger and they can offer different kind of services. And also, the whole strategy, it's a bit different and very different than the heating for industry, where the demand is not weather driven, but driven by businesses and industrial processes. And the flexibility, it's much different, the strategy. And also the heating for cooling, that it's an increasing sector in demand, especially in the view of climate change. Much more cooling needs. Here we have similarly, as I presented the California case, an example of a very successful initiative in Tarnby city of Denmark, while they implemented one of the smartest district heating and cooling systems that integrates heating, cooling, electricity generation, thermal storage, and also takes advantage of waste heat from water treatment plants. So looking at their model, we also identified what innovations they used and how they combine and build their strategy for a successful project. I will not go in depth to this, but I would like to focus here as well on the blind spots. We identified here as well a number of things that we find them important, aspects that we find them very important, but often overlooked in our discussions with stakeholders and policymakers. First is the temperature, which is a critical variable in designing a smart electrification strategy, as already mentioned. Hybrid heat pumps often overlooked, but are a technology that offer an interim solution to rapidly introduce heat pumps in buildings with existing gas infrastructure and might have a higher acceptance rate in the consumer side during this not a drastic change. Then thermal energy storage is a technology that has significant potential to increase the power system's flexibility. It's not so much of an innovation in terms of technology, but it's not used enough, and now their usages are much more important than before in providing flexibility on this demand segment. Digitalization, it's at the core of a smart approach, and it's always very important to collect, monitor, and have the data in order to control and to make decisions on the smart operation. Cooling demand is growing and should be more and more considered in energy planning due to climate change and increasing temperatures that we witness. Building codes offer important incentives for smart heating strategy in the residential sector. And last but not least, energy efficiency and waste, heat, and cold recovery should be a key part of smart electrification strategies. With that, I would like to conclude a number of key takeaways just to summarize everything that I said so far. So yeah, as mentioned, the bulk of the energy transition relies on renewable electricity as main energy carrier of the future. There are two main challenges that are addressed by this analysis: how to accelerate the energy transition through innovation and how to electrify new sectors while minimizing infrastructure costs and optimizing power systems. Smart electrification creates a virtuous circle while end-use sectors are decarbonized and also are new loads that become flexibility option for the system to integrate higher share of variable renewables. We need systemic innovation in all these four dimensions: technology, regulation, system operation and planning, business models. And we have mapped 100 innovation in this report. I presented today 70 of them in mobility and heating and cooling, and we have another section of 30 innovation for how to operate smartly the electrolyzer to produce green hydrogen that are not covered here, but in the report you can find more details. Now I will hand over to my colleague Adrian, who will present to you why smart electrification is important and what is the benefits actually for the grid in a more quantified analysis.
Thank you, Arina. Welcome, everyone. Yeah, with the aim of analyzing the benefits of aspects of smart electrification in a bottom-up approach, we have designed a model of the power system of a simple residential neighborhood with the standard grid that I will show in the next slide. Here you have it. In it, we have launched optimal power flow calculations in different scenarios, from generic non-smart consumption to several solutions applied simultaneously from the ones my colleague Arina was introducing before. The target of the optimization is to minimize losses in this small grid, as this is a key criterion which leads to a demand curve flattening. Let's dive into it in the next slide. So the assumptions for this analysis include a moderate projection of deployment of heat pumps and a conservative deployment of electric vehicles and rooftop PV. You can see in the upper left part the status on 2020 and the forecast for 2050. So the mid column is the one we used for our case study. Below you can see the monthly shares of base load considered as non-manageable demand and the three mentioned elements, which are the only ones providing the smart electrification in this analysis. So we are not considering any additional battery storage in it. Then we have defined 6 scenarios, including one or several of these elements to assess their impact. We have the V1G scenario, where the electric vehicle behaves exclusively as a manageable load, the V2G scenario, where the electric vehicle has bidirectional capabilities, meaning that it can reinject electricity in the grid, and an iteration of the V2G in which the converter also provides voltage regulation to the grid. Another scenario, the thermal flex, does not have electric vehicle charging, but a smart management of the heat pumps to maximize the efficiency of the system by using the inherent thermal storage and the thermal inertia of the buildings. Finally, we have the smart scenario, which benefits from the combination of the most sophisticated electric vehicle options, so the V2G and voltage regulation, plus the optimization of heat pumps as in the thermal flex one. You can see the different demand day curves in an average day for each of the scenarios in this residential grid. So what are the results of this exercise? First of all, as could be inferred from the previous demand curves, we see reduced loads in the power lines in the peak hours. In the main graph here, you are seeing the maximum currents in each grid element in each scenario. For example, the first one shows the element linking the nodes 0 and 1 in the model, which in the base case reaches almost its maximum load, and in the smart case, it only reaches around a 50%. We have also some smaller graphs in the upper right side, but I think they are not plotting very well. Well, they represent more or less the same idea, where we see that the occurrence of these maximum loads is notably reduced along the year. The evident conclusion here is that while in the base scenario, the distribution grid needs an urgent reinforcement because of these loads reaching almost 100% of the maximum accepted in the power lines or transformers. If we implement the smart approaches just through these heat pumps and EVs, we delay or reduce the need for upscaling the distribution grids. A second consequence of this reduction of peak power flows through power lines and transformers is that the losses through these elements result halved. The main reason is that the thermal losses increase quadratically with the current. So halving the current at peak hours has a major effect in losses reduction. So it has an associated global efficiency effect for the whole system, also leading to reduced prices thanks to an electricity that is not produced, not paid. And last but not least, the effect of transferring load out of the peak hours results in a global effect on the electricity prices. In most electricity markets, the price paid by all the consumers is defined by the marginal price, meaning that the offer of the last megawatt hour generated is the one defining the global price. Therefore, avoiding generating this small addition of peak power of power at the peak hours result in a notable effect in the price reduction. Also, it can be seen here the different technologies that contribute to the price formation. So you can see that the most CO2 intensive ones are the ones typically offering at a higher price. So it's not only a gain in terms of price reduction, but also in emissions associated to the whole mix. So yeah, I give the floor back to my colleague IRENA that will wrap up the next slides.
Thank you very much. So just to wrap up, I want to mention that I leave here all the links to our innovation landscape report. We actually have two. One that was released earlier and focused on innovation to integrate high share of renewables in power system. And I think it also was an input for one of the mission's knowledge products. And the more recent one that I presented on innovation landscape for smart electrification. We also have a digital version of this report, kind of easy navigation through all the content. So please feel free to go on our website, and if you don't find it easily, I'll leave here exact links to the pages. And I also would like to mention here the fact that last year we had the IRENA Innovation Week here in Bonn in September. And I'm saying that because it was a nice conference, but also all the recordings are available on our website of all the sessions, and also a summary report. It's available with very nice key insights and summary for all the discussions of three-day sessions around, again, the decarbonization of end-use sectors and the smart electrification strategies. I leave here the 6 main actions to enable energy transitions as a result and a summary from these discussions at Innovation Week. First, very important, we noticed from the discussion and the stakeholders to de-risk investments in innovation. Second, address infrastructure challenges are often overlooked. Prioritize demand-side management strategies. Here it's where most of the smart electrification strategy fall into. Also create demand for green products, especially in the hard-to-abate sectors. Ensure equity and inclusivity, and cooperate for robust supply chains and technology and knowledge transfer. As I said, much more information around these 6 actions are in our summary report, and also you can check the recordings also on this link that I left here, innovationweek.irena.org. Thank you so much. Okay, I have a video here, but I've been informed that it's not working for all, so I will just leave it here. Thank you so much, and we're happy to answer any questions if there are.
All right, thank you very much, Irena, Francisco, and Adrienne. So we'll go straight into the questions, and I think I will use my host privilege to ask the first one. So I was curious about the couple of case study examples that you gave. So there was the California one for the power to mobility, and there was the city in Denmark with the power to heat and cooling. And I was just curious if you have any other examples where they've tried to implement some of these innovations that you've mentioned in your report, but it's maybe not gone so well, and what kind of lessons have been learned along the way that can help other cities trying to do these innovations but haven't quite got there yet. Some lessons learned.
Yes, good question. So the report is full of examples. For almost each of the innovations, we bring an example of where it was implemented. Usually it's a good example that worked well, but we acknowledge also the importance of sharing practices that didn't work well with lessons learned. I think many of them are actually summarized in the blind spots. This is what how we created the blind spots based on examples or situation on case studies that something was missing and didn't go well. So we created this blind spot list. But in terms of really showing the location and exact details of the case studies that didn't go well, I think it's something we don't present in the report. I don't know if Adrian, you have an example maybe from the top of your head. No, I saw that you.
Okay,
I don't know.
no problem. In that case, we'll move to one of the questions that's...
Francisco, yeah, sorry,
Oh,
Francisco, I think he
go ahead.
Yeah.
Thanks, Craig. I think that your question is quite important because one thing that we need to better understand is what is not working to improve. So two comments there is that on the one hand, the issue is that we are really in a learning phase. That's why these are innovative. So many things are being tested, and in some cases it's a little bit early to really say that something has say failed or succeed. We are really in a process of learning. But on the other hand, there are really challenges that we have seen. I think that's what Sarin explained. We try to put in the blind spot. But one that is kind of common is actually the disconnection between the different innovations in what we call the systemic approach. For example, some countries really focus on deploying infrastructure for charging electric vehicles, and have the capability for vehicle to grid. But on the other hand, there is no, we can call it implementation of an innovative real dynamic pricing. So you can have the technology and you can have the capability to provide services to the grid, but actually, in some cases, it was not happening. And there are a few cities where it happened. And basically, the issue is that there was no regulation accompanying that technology innovation to really make the business case for the aggregator to come and build up a business model. So I think that if there is one common area of I wouldn't say pitfall, but let's say area that to be really better considered is how to make these different aspects of the systemic innovation approach to work together, because one without the other will not work. So and the other thing that what is also I think we feel very proud about this project is that for each one of these three vectors, we had a series of consultative meetings between 40 to 60 experts for mobility, for heating and hydrogen, actually sharing these experiences. So what you will find in the report actually is the outcome of these let's say consensus among these experts on what are the key innovations and what are the key blind spots for these sectors.
Yeah, thank you for that. That's a really good answer. I think very important to make sure all the different sectors are connected. And that's one of the reasons the GPFM exists. And hopefully the webinars like this one are achieving what you're talking about there. Okay, so we'll go to the chat now. And remember, if you want to, you can raise your hand and I can unmute you. I can allow you to unmute and you can ask your question. So feel free to go ahead and do that. But we'll come to this question from Leonardo. He says, last mile infrastructure is a critical factor of success. What about the regulation to use certified materials in order to improve energy efficiency? So who wants to come in on that?
Yeah, sorry. Maybe I can start and then the colleagues can add. But fully agree with Leonardo. Energy efficiency is crucial. And let's say the decarbonization with electrification has to go hand in hand with energy efficiency. Two concrete comments on this. The first one is that electrifying end use or replacing combustion of liquid fuels with electrification already represents a significant efficiency gain for the system. I don't know, Arina, if we can go to the second slide when we have the energy mix in total final energy consumption, because there you can see really the benefit of electrification, where you can, yeah, this one, where you can have in 2050, of course, more population, economic growth in the planet, but you can see that total final energy consumption is lower in 2050 than 2030, from 374 to 350 exajoules. And a big share of that energy efficiency gain is thanks to electrification, because the exergy of electricity as a vector is much higher than other energy vectors. So that's one aspect. And the second on the certification on using the best available equipment and the highest efficiency equipment, some calling labeling schemes or tag schemes is critical. That's also included in our report because electricity has become such a valuable energy vector that every electron has to be used in the best possible way. So definitely energy efficiency goes hand in hand with the smart electrification. I don't know if the other colleagues would like to add.
No, I think it was complete actually. No.
Okay, thank you for that. And we'll move on to the next question. This is from Alexander, who has two questions actually. So I'll read the first question. When speaking about decarbonization of road transport, you are taking into consideration only charging and corresponding electricity demand. What might be the implications of innovations within the vehicle production life cycle, and if those might affect life cycle emissions? Who wants to come in on that one?
Should I start or you
yes,
can?
please,
Okay,
Arena.
you can go.
No, Arena, please go ahead.
So yes, we are aware that there are many facets of electrifying end use sector. The focus, exact focus of this report is actually to look at smart charging and how to couple the power sector with the electric vehicles and how to take advantage with smart operation of charging and smart charging, yeah, to enable a lot of benefits in renewable integration and minimizing grid infrastructure on the power sector side. Having said that, what might be the implication of innovation within the vehicle production life cycle, and if those might affect life cycle emissions? Yeah, we didn't really look at this part because it's out of the scope. Vehicle production life cycle. We have this report coming out, yeah, on critical materials, but maybe. Okay.
Mm-hmm. Yes, exactly. So
yeah.
The question about life cycle analysis for vehicles is out of the scope of the smart electrification. But as Irina mentioned, actually in more or less 1 month from now, we will release a new report on innovation on critical materials for the production of batteries for electric vehicles, where we look into that. But as a sneak preview, which I think is actually already in quite a number of scientific papers, is that there is more consensus and based on data that doing a complete life cycle analysis comparing internal combustion engine cars and electric vehicle battery cars is despite let's say the first perception that maybe batteries at the end of their life may cause a significant increase in waste and residues. The full life cycle analysis shows that still electric vehicles have significant environmental gains. Not only because basically what we are looking to materials for battery electric cars, it's really marginal in comparison to the amount of oil that has to be mined to fuel those vehicles, but also because of great advancements in recycling and second life uses of batteries. So at the end of the day, the waste that may have from electric vehicle batteries, etc., is really small in comparison to the impact of exploiting and mining oil to fuel internal combustion engine cars. And on the second part on the parking time, We look into a global average parking times, but we differentiate between the modes, the three modes that IRENA mentioned. So it's very different, the parking times for passenger cars, for light commercial vehicles, for heavy duty vehicles, and for electric buses. And that was taken into consideration in the analysis to see exactly when and how long these vehicles could be parked and available to charge, but particularly to provide services to the grid.
On
And
this last
adding,
one,
yeah,
sorry.
sorry. I wanted to add to this question that actually it's on the parking times. The main methodology we used, it's a lot of stakeholder engagement. The consultative meetings we had with a larger group and also bilateral one-to-one meetings with different sector representatives, also from Global North, Global South, different mobility segments to understand how they operate and what is possible for them and what not in terms of smart charging and services that they can provide to the grid without affecting their main business, let's say, in terms of e-trucks and light commercial vehicles especially. Sorry, Adrian, I interrupted you.
No worries. No, just wanted to mention very briefly that in the model I presented before, it's important to highlight that there is a lot of benefit for the distribution grids on having the possibility to charge the electric vehicles, so the light passenger cars, not only at the houses and at the parking spots of the houses of the residential buildings, but also at the working places. So with this, you benefit from the services, especially from the bidirectional charging or bidirectional capabilities and the voltage regulation most of the time of the day, because you consider that the commuting times are just a fraction. It doesn't make sense to have to unuse, let's say, the vehicle during all the working hours that the worker can have the car parked at he or her working place. So for this, the regulations are again important to promote the development of these charging spots also in the working places.
Okay, thank you for that. I think some of what you were just saying might partly answer Luciano's question here, but I'll read it anyway. So Luciano, the director of the GPFM, says that he believes the EV section that you did is a must. Different vehicles have different charging needs and different profiles. And we did an extensive work on this in 2023 and would be happy to compare results. And he asks, did you also do some analyses or estimations about an optimal sharing from the transmission and distribution network point of view among public, private, and domestic charging?
Yes, well, first of all, thanks, Luciano, for the good question and also for the good cooperation between IRENA and the Green Power Future mission. On your question, yes, in IRENA we have looked into this topic, and we haven't updated in some time, but what we have seen is that on average there are between if you have 10 charging points in a country, between 3 to 4 are public, and between 6 to 7 are private. Now, having said that, of course, the level of the power of each one of these charging is different. The ones at homes, of course, are in the range of maybe 7 kilowatts, while you have public is 30, 50. Now we have even higher for fast charging. So the implications for the grid are different. The second point is that the impact is mainly on the distribution grid, not so much on the transmission grid. Now that we are having larger, maybe even considering in the future, up to megawatt charging points for heavy-duty vehicles in resting areas close to highways, there might be implications for mid and high voltage grids. But as of today, the incumbents that are more affected by this are the distribution system operators and the distribution grids. That's why the main focus, for example, on the case that Adrian presented was also looking into distribution system, because it's where you would have the need for the highest investments. Yeah, and we also did an analysis of cost benefits between smart electrification and on-control or dome electrification in a city, using the case of one city in Germany. And basically, our analysis indicates that the investments required for smart electrification are, or better, for a dome electrification are 10 times higher than with smart electrification, mainly because with a smart electrification approach, the main investments are in digital infrastructure, not so much on copper, while with an on-control is mainly copper. So you will have also transformers, switch gears, etc. So it's in the ratio of more or less 1 to 10, the difference between investments for smart electrification and on-control electrification, without taking into account also the time that it would be needed for a distribution system operator to change cables, to, if it's underground cables, to break roads, to close roads in the city with all the implications for the citizens. So it's really a big change between, a big difference between a smart and on-control electrification approach for electric vehicles. But happy to compare notes with you, Luciano, on this.
Okay, thank you for that answer. Now we have a question that's popped up in the Q&A section. This is from Anurag Verma. So on slide 4, electricity consumption by sector has been discussed, and there you see that green hydrogen is shown as part of consumption, but here green hydrogen is a source of energy, so they are a bit confused as how it is consumption by sector. So I think just a little bit of clarification needed, perhaps. So who wants to take that?
Maybe I can take this one as well. Yeah, the issue with hydrogen is clear. That's a very good question, because now you see, including IRENA, that we present more and more demand or like a segment for energy demand hydrogen, while it is indeed it's an energy carrier. But basically, the main uses of this green hydrogen would be for synthetic fuels, so basically shipping and aviation fuels, for the chemical sector, for fertilizers production as a chemical block, and the rest would be mainly for long duration energy storage supporting power systems. So these are the main uses for all these green hydrogen. Actually, we have other slides where we break down this demand for green hydrogen, but of course, because of the time we have, that's not really the topic, we didn't include it here, but we have also a breakdown of those. And I think the others are clear. Industrial applications, mobility is mainly electrification of road transport. It does not really include electrification or direct electrification of shipping or aviation, despite we are aware that now there are some advancements for short-haul aviation and shipping, like ferries and small planes. And buildings is mainly heating and cooling services. Cooling already applied with air conditioners, but heating a lot of additional demand from heat pumps and to some extent electric boilers as well.
All right, thanks for that. I'm not seeing any more questions popping up in the chat, but I did have one more, and this is for all 3 of our speakers to take turns to answer. So my question is, in your personal opinion, from what you've, all the knowledge you've gained through doing this report and all your work at IRENA, in your opinion, what is the next big technology in the power to X, whether it's heat or cooling or mobility? What is the next big technology in that sector that is still in a low TRL level at the moment, but you see becoming a very big part of the power system in, say, the 2030s or the 2040s? So in your personal opinion. So who wants to go first on that question?
Maybe I can go first. Because I will answer the question, but not straightforward answering your question, because I do feel like we have most of the technologies available today for the transition, and I don't think we need a lot more innovation in technology. They are here, but as we mentioned also, Francisco, in the presentation, we need much more innovation in how to integrate and how to make best use of these technologies in order to advance the transition, and how to, in regulation, in planning, and how to ensure the revenue stream so they are further deployed and further and smart operated in order for the energy transition to make sense for everybody, and to both private, public sector, and also reach the targets we are far behind. I don't think technology is a burden, and I don't see a big technology coming. It's more like more cooperation from all the stakeholders and aligning on what incentives need to be sent in order for these technologies to be best utilized and to best used for the advancement of the transition. That's my 2 cents on this. Thank you. Very nice question.
So Francisco, did you want to come in next? What is your answer to that?
I think that, as Arina mentioned, for the bulk of the energy transition, we have already commercial technologies available. However, for some applications, there is still some technologies in early stages that we will see. And to mention maybe two groups there, one is digitalization. I think digitalization in the energy sector is not fully understood the role and also used to the extent that it can be used. I think we are just scratching the surface on how digitalization can really be used in supporting the decarbonization of the energy sector. And the other is for some of what is the so-called hard-to-abate sectors. There are some interesting and promising technologies to directly electrify some applications that before were seen like impossible to electrify. Just to give two examples, in the steel manufacturing sector, for example, molten oxide electrolysis, which basically is using electricity to produce extremely high temperatures to actually be able to melt and reduce iron ore for the production of steel without the need of blast furnaces. So this is one. And another one is, for example, chemical crackers for production of high value chemicals, which are fueled by electricity directly without need of, as used today, natural gas. There are already some countries piloting these e-crackers in some countries. By the way, we published 2 months ago a report for the Italian G7 presidency, where they asked us exactly that question. What are the emerging technologies that can help to decarbonize the hard-to-abate sectors? That was published. Maybe if Arina or Adrian could put the link in the chat, and you will have all the details on those emerging technologies for hard-to-abate sectors in that report.
Yeah, great, thanks. That link will be very useful, I'm sure. And then finally, Adrienne, did you have 2 cents on this question?
Yes, mainly to echo what my colleagues already said, because I do believe that despite the innovation in technology should be maintained, what's really an urgency is to innovate in the way we implement these innovative technologies. So regulatory frameworks, innovative operations, the power systems, those are really the aspects we should stress in these immediate years. Also having in mind the tripling target for 2030. So yeah, those will be my 2 cents.
All right, great. Thanks a lot. No more questions have come through in the chat or the Q&A. So if there are, oh, just as I say that, another one has appeared. This is also from Anurag Verma. Is IRENA also studying the role of greening city and buildings by nature-based solutions in reducing demand for energy in heating and cooling? Who wants to come in on that?
Maybe the short answer is yes. So we are looking, not our team, but some other colleagues here in the IRENA Innovation and Technology Center are looking into that. We recently had a webinar with actually Mission Innovation, I don't remember the name, Craig, but maybe you know, I think it's the Urban Decarbonization Mission. It's one of the 7 that you presented at the beginning.
The Urban Transitions Mission.
Correct. We had one with them, and actually, I think the webinar recording should be available. But yes, we are looking to a comprehensive approach for decarbonization of cities as well. Mm-hmm.
Okay, great. I'm sure that's available on the Mission Innovation website under the Urban Transitions Mission. All right. Well, if there are no more questions, we have been going for a while, so I think we'll leave it there. So just before we finish up, I will quickly share information about the next webinar. So hopefully you can all see that. So next month on the 6th of September, at the same time of day as this, we will feature our colleagues from Spain, one of our main core members to the mission. And they will present 2 different pilot projects that they do. One of them is called Synergies, and one of them is called InSit EV. And if you scan that QR code, you can find out a little bit more about them. But just look out for the email of that coming very soon. And also, as soon as the recording of this is available, I will also send that out to everyone. I've just noticed there's another Q&A question. Oh no, it's a comment. Just saying thank you for that last question. All right, so I think we'll finish it there. So thanks very much again to IRENA, Francisco, and Adrienne from IRENA, and thanks to everyone for attending. And we'll see you at the next webinar. Thanks, everyone.
Thank you.
Thank you very much,
Have a nice
Craig
day.
and colleagues. Thank you.
Thank you.